All right, so welcome to what I was planning to do on Tuesday before we had some technical difficulties. Let us review then what it means to have a constant rate of change, what we talked about on Thursday, the first day of class, and then we're going to go over some vocabulary quickly. This will be more brief than what we did in class. I know you saw this already, but let's get an overview of what we talked about and maybe some more high-tech visuals for a change. So, constant rate of change, what we talked about, this was again from the end of class Thursday, using changes in the independent variable. So dx, or x is the independent variable. Dx represents a small change in that to determine dy. Y is the associated dependent variable. So dy is a small change then, or an amount of change that's associated with the dependent variable when the independent variable changes by an amount dx. So you're filling up your gas tank and the gas costs $2 per gallon. And so we talked about what is the meaning of $2 per gallon, the constant rate, other than it would be a great price for gas. Said every additional gallon means $2 more in cost. Kind of a basic definition, easy to start from, but then to have a more comprehensive meaning, covers more bases all in one. Instead of just talking about 1 gallon meaning $2, we can expand that to talk about for any additional gas purchased. So whether we're starting from the beginning or you walk up to your friend when they've already been filling their gas tank for a while, for any additional gas purchased past a chosen point in time during the gas getting process, the extra cost for that is going to be 2 times as much. The gas purchase is measured in gallons and the cost is measured in dollars, but the numerical components of these are different by a factor of 2. This 2 is that constant rate. Doesn't matter in this case if it's a small amount of extra gas purchased or a large amount, however much additional gas is purchased, multiply that number of gallons by 2, and you get the additional dollars that are added on to your previous purchase price. So here's the gift box example we were talking about. I think I have slightly different numbers, but let's say that the box that we're buying to put our bulk candy into a box, the box costs $B and snack mix costs $2.75 a pound. So chocolates, peanuts, whatever it might be. This means that using our same sort of general translation, not just 1 pound would cost $2.75 or 2 pounds costs $5.50, but any additional number of pounds added into the gift box would increase the cost of the gift by 2.75 times that number of pounds. The cost would be measured, however, in dollars. So thinking about defining our symbols that we've used in these sorts of problems, if I want to talk about x, y, dx, dy, m, let's start from a general so we're all in the same place, x being the number of pounds of mix in the gift. So then if that x, our independent variable here, is the number of pounds of mix in the gift, the other quantity that we're measuring here is the cost of the gift. So let's let that be y. And then so looking dx and dy, make sure you realize that these are related to one another, obviously, but x is talking about the number of pounds of mix in the gift, like the total number of pounds at any point in time while you're in the store purchasing this gift. Time isn't something that we're measuring here, but if you were to walk up at any point in time, x is the total number of pounds in the gift, or when you go to the register, that x is the total number of pounds of mix in the gift. Whereas y is the total cost for the whole thing, the box with x pounds of mix in it. Dx and dy aren't about the total amount, they're about an incremental change or a variation in how many pounds of snack mix, gift, candy mix, whatever it is that you have, are in the box. So if we put a little bit more in or take a little bit out, that amount that we alter the weight by, that is our dx. Dy is the associated amount that the cost changes by. And those two, as we talked about, are going to be related by this number 2.75. So the change in the weight of the gift, or how much we let that weight increase or decrease, or how much it varies while we're scooping in a little bit more. dy is the associated change in the cost of the gift. By putting in this extra, the cost changes as well. And so if you want to imagine pouring in like a little half scoop as it changes, so dx isn't just one numerical value. Dx can start from 0 as you pour in more candy, increase from there by a small amount, and at the same time, dy, an associated variable, is also increasing. It's increasing at a rate that's 2.75 times as much. So, or by an amount that's 2.75 times as much, rather, because m is this rate of change, $2.75 per pound. So 2.75 times as many dollars change as there were pounds change from whatever initial amount you might have known about. So here's the thinking about negatives or positives. You can put more mix into a box, you could take some out, but suppose that after scooping some mix into the box, you decide you want some more. The additional cost you'll pay for 1.5 more pounds of this trail mix or snack mix is $2.75 times $1.5, right? So let's think about this relationship, dy equals mdx, and what this has to do with any of that. Well, in this case, we can see, and let me see if I can get this thing working. It usually cuts out my PowerPoint for the first time I try, so we'll see. Yep, as usual, but it'll work in a second. Here we go. So dx, change in or variation in, increase in x, our independent variable, the thing we get to control here, how much trail mix we're using, or snack mix, whatever I was calling it. So the value of this then, how much more, how much do we let it change by or vary by? 1.5. Now this is measured in pounds. The associated change in price, now we can multiply this out, or I can just say, oh, it's 2.75 times that 1.5. And the units on this is our cost, the associated increase in cost when we increased the weight by 1.5 pounds is 2.75 times 1.5, well, dollars. We'll probably have dollars and cents by the time we're done. But M is representing this rate here. So this is just the 2.75. The units on it are dollars per pound. So each of these have numerical values, and they also have units. But just make sure you keep in mind that we're not concerned here about what's the total cost of the gift with all this extra in it. All we're talking about here are just the related incremental changes, not the total price. So not x and y, but just dx and dy. All right, so if I were to change this problem, and this time you're like, that's a little bit too full, I'm going to take out some, scoop some back into the bin, and hope that the cashier doesn't care. If we wanted to talk about these values, well, it's the same situation. M is still this $2.75 per pound, or $2.75 per pound. But dx and dy, if we're removing 0.4 pounds from the bag, or the box, whatever it was in, that's changing. But if I just put 0.4, I know here I do, oh, well, that's 2.75 times 0.4. Notice that we're removing this. We should be paying less. So keep in mind these changes, although we've only talked about positive changes or increases so far, you can have decreases or negative change, so that dx, an incremental change in the number of pounds of candy in the box, decreases by 0.4 pounds. That makes our cost also decrease, not by $2.75, but by $2.75 per pound when we have 0.4 pounds that are going away. So, like whatever this comes out to be, around $1, so $1.20. But this is dollars. It's a decrease in our cost because we decreased the weight. So keep that in mind when you're working with decreases. It's very easy to forget the negative signs because we're just thinking in our mind about how much change there is and thinking about the absolute value, just the size of the change without considering the signage of it. One of the most common mistakes I see in homework and test sorts of situations. All right, so one other situation. Here we go. A soldier lowers an American flag from the top of a pole at a rate 0.75 meters per second. So, again, translating this means that during any interval of elapsed time, in seconds, the height of the flag, measured in meters, will decrease by 0.75 times that amount of time that went by. So 1 second goes by means the flag would be lowered by 0.75 meters. That's the boring way to interpret this. But so we can be more general or cover all of the situations that are covered by this up to a certain point in time when the flag finally reaches where he stops lowering it and the whole military organization holds on to the flag and folds it up. Up to that point in time, it's lowered at this nice constant rate. So if we let y be the height of the flag, meaning a height of the flag above the ground in meters, so that we're all starting from the same point, think about each of these 5 variable expressions or parameter in the case of m and what this would be. So, as we said, y is going to be the height of the flag above the ground. So if we were to look at the rest of these, if y is the height of the flag, measured in meters, I'm just going to abbreviate here, what's the other main quantity that we're relating to height here? Oh, well, we've got time measured in seconds. So x must be the total elapsed time since he started lowering the flag. So I can say height in meters because, well, it's all written right here. The height of the flag above the ground in meters. When you're defining something, make sure you're precise. Like x and y, these overall or total variables, there's generally some sort of starting point, like the height above the ground, the time since we started lowering the flag. So this one I'm just not rewriting because it's right there. But x then, if I want to say this, I don't just want to say seconds. Seconds isn't a good enough description. We want to talk about, if we want to be really precise about it, I'm going to make this a little bit thinner so I can write a little bit more. This x here, we're measuring in seconds how long it's been since the flag left the top of the pole. So I'm going to say the time in seconds. Since the flag left the top of the pole, or since the soldier started lowering the flag. So if I just wrote time, that's not enough. If I just wrote seconds, that's not enough. I need to have time or seconds of what? So this y here, the height of the flag above the ground in meters. Make sure you have the quantity that's being measured, the units that you're using, and in the cases of x and y, these total value sorts of variables, we also want to have a relative point. Relative to what? Since the flag left the top of the pole, or height above the ground. Now, on the other hand, be careful not to overuse that strategy. dx and dy are talking about not the total value since the beginning, just a change or a variation or an extra amount or a small decrease. In this case, dx is talking about time and how that varies, and dy is telling us something about height and how that varies. So dx would be a little bit of this time. So I can think about it's not since we left the top of the flagpole. This could be at any point in time. If you want kind of a visualization of what's going on, if I were to imagine graphing my time measured in seconds this way and the height of the flag above the ground this way. I know that it starts somewhere up. I don't have a height listed here, but it starts at some height above the ground, going downward at a constant rate, and we know that looks in XY axes that are scaled equally, this shape. So this dx is something that I could measure from any point. If I go forward a little bit in time, or I could go backward, but just normally how we think about if it is this time is go forward a little bit in time. If a little bit more time goes by, then the height will decrease a little bit. So visually speaking, our dx and our dy could be seen in this graph here. I could make dx bigger, and dy would also be bigger. It would be bigger proportionally, though. I could put them in a different spot. They don't have to be starting here for any reason. I just picked a spot somewhere in the middle of that line that I drew. But dx is a small amount of elapsed time. Still measured in seconds. The units aren't going to change. So I could just say it's a small amount of elapsed time, or, ooh, sorry about that. Let's get this pen working here. Small amount of elapsed time. So if dx is a small amount of elapsed time, it's not from when the flag started moving or anything like that, just a small amount of elapsed time. Could happen at any point during the descent of the flag. We let time vary by a small amount. Then dy is the related small amount of decrease in the height of the flag. There's a lot of different ways to phrase these. There are just some aspects that need to be there or need to not be there. Now, both of these, I'm going to go back and put the units, because although it's a small amount of elapsed time, unless I want to start doing unit conversions, I'm going to measure this still in seconds, and I'm going to measure the flag height changes in meters still. We could obviously change to whatever units we wanted to, but just to make it simpler, we'll just keep using the same units for those. But m is not a relative to anything. It's just our constant rate. It's this 0.75 meters per second. It's the decrease rate of the height of the flag as time goes on. So notice when I wrote these, I wrote that dx is a small amount of elapsed time in seconds. I wrote that this is a small amount of decrease in the flag height. It could be an increase if I imagine like going back in time. So you might want to just talk about small amount of change in the flag height. It could be positive or negative depending on the value of this. Just typically speaking, when we're talking about something where time is the independent variable and you're just watching something happen, time goes on, time goes forward. And then we talk about what happens to the dependent variable as time goes on. But we can talk about it in either direction. So I could say a small amount of change or variation in the flag height to be more neutral about this, or to make it apply in more situations. But lots of times there's one natural direction for something to go when time is related. And as time goes on, this is decreasing, so I want to make sure I get this negative rate of change. When we write it in a sentence, we can say decrease by 0.75 meters per second. You could have also written in this description, or I could have written, that it changes by, the height of the flag above the ground changes by a negative 0.75 meters per second. That doesn't sound quite as much like casual conversation. It sounds more like math book, but it could be written that way. But just keep in mind, if you see these rates of decrease, if you're going to be assigning values to symbols, that would go with a negative. All right, so let me clear these off of here. Boom, gone. All right, so here's some slightly more neatly typed definitions of these. But again, there's a variety of ways that you can explain these. There's not one set of words that you have to use all the time. But just again, to point out this, since the flag left the top, or the height above the ground, the general independent and dependent variables, they have points of reference. These, the changes in those, or the variations in those, as we look between points close to one another on the graph, or if we think about points in time, or it doesn't have to be time, this one happens to involve time. It's just a variation, could happen at any point in the situation, doesn't have to be since the beginning. So we don't include those since the beginning sort of situation descriptions in those. All right, so if I wanted to talk about how much does the height, still the flag situation, vary between 4 seconds and 6.9 seconds since the flag left the top of the pole, this is, again, and if it helps you to visualize, certainly, this is not cooperating today. Certainly, you know, sketch yourself a picture. What is this talking about? Between 4 seconds and 6.9 seconds. What's going on? Well, I had this flag. It was going downhill. This is its height and time. This isn't an official, well-labeled, but just sketch yourself something that'll help you visualize what's going on. Between 4 and 6.9 seconds, during this small increment of time, which you can subtract, say, oh, that's 2.9 seconds. During that 2.9 second interval, how much did the height of the flag decrease? Well, it decreased by, according to the information on the previous page. Come on. Let's see if this is going to work. 0.75 times this amount of time. So if this is our dx, this is dy, otherwise known as mdx, or negative 0.75 dx. If dx, the change in the amount of elapsed time, or a small incremental amount of time that's gone by. If dx is 2.9 seconds, then dy is going to be negative 0.75 times 2.9, and the units on that are meters. So, not quite sure what this is. Let's see, about 0.8 or so. Right, 3.7, 3/4 of 3, whatever it comes out to be. But it will be measured in meters, and it'll be a negative number. So all of this put together, dx, dy, and m, oh, well, in this situation, dx is 2.9. We can get that by subtracting. dy is the same as mdx. dy and dx are in a constant rate of change relationship with negative 0.75 as that constant rate. So we've got this negative 0.75 times 2.9. And then, so m is the negative 0.75. They're in this relationship. So we could compute this out, or we can just write the relationship. Now, what I do want to talk about briefly, something in the textbook that's pretty cool. It shows up in a few different sections, one of which is section 3.15. I think it's 1.5 and 4.1 also. It's all over the place because it's really cool. Let's see. We'll get to variables, constants, and parameters in just a minute. But in section 3.15, we're talking about envisioning constant rate of change. So there are two different animations in this section. Instead of having an XY plane and graphing, we just have two number lines. One number line representing X, and you can see incremental changes already happening before I start playing it. And the other one representing dy, which is, in this case, we have positive values of m. So we've got incremental increases in dy that are also positive going to the right as we play this. You can see this is set with m equals 1.6. So this is a parameter for this graph. Suppose m is 1.6. Let's see what happens as x and y vary. Well, as x and y vary, I can imagine adding on little incremental bits of change, little additional time, a little bit of additional weight of candy, whatever it might be, a little bit at a time, and that increases by a multiple m dy as well. So we have m as positive numbers here. It's the only way the graph is going to go to the right in both cases. Now, we have larger values for m, smaller values for m, but m maintains one value as we let x vary, and that causes y to vary because x and y are in this constant rate of change relationship. So this is just demonstrating a bunch of different values of m, and we can see these. So notice that b that's up at the top, whether you consider that, oh, that's the weight of the box that we were putting the snack mix in, or not the weight, the cost of the box they're putting the snack mix in. So that the green and blue added together would be the total cost of the box of snack mix, whereas X is the number of pounds of mix. Whatever you want to envision this as, notice that this equation here just relates the X and Y are in a constant rate of change relationship. That means that dy, the incremental changes in y, are a multiple of the incremental changes in x, or as we let x vary, and in this case become larger and larger, adding on a little bit all the time. Depending on what m is, it looks different, but we have y also increasing by little bits of dy at a time. So the b doesn't change. That just sits there. And notice that b isn't in this equation. The changes in y don't depend on what b is. The changes in y don't depend on what y started as. It's not relative to some beginning point. It's just a multiple of an incremental small change or variation in x. All right, there's a second graph just below this that shows maybe the familiar slope-intercept form of an equation, y equals mx plus b. So here is a picture where you can see the y and how y does involve knowing what b is. We can find y final, this value out here, by finding this mx and adding it on to b. So this graph isn't emphasizing the relationship between the incremental changes, although you can still see them, but it's labeled different parts. So let me go back to when there are slightly larger changes. It's a bit easier to see. So you can see in between these little gray lines, you can imagine each of those as x varies, I'm adding on little pieces, little amounts dx at a time. I'm just marking it every so often so you can see the relationship. Here's a little bit down here, corresponds to, well, right now, 1.9 times as much, a little bit extra up here. So this mx here, this isn't the same as mdx. This whole blue section here is all of the change in x from the beginning, so x multiplied by m. Now, this b is still not a part of it, but in order to find a final value of y, I need y initial plus m times, well, all the changes in x. All the changes in x, we're using the same constant rate, so I can just call it mx. So these are slightly different graphs from one another. This one's emphasizing the final value of y, whereas the other was more just emphasizing the relationship between changes in x, variations in x, and the associated changes or variations in y. All right, now let's take a break from this and go back to some vocabulary. Let's see. Nope, that's the constant rate of change one. Here we go, variables, parameters, and constants. So some vocabulary to make sure that we're all using the same words to mean the same things. A variable is a letter or a notation that takes on the value of a changing quantity in a given situation. So variables vary, in other words. Variables aren't things that have one value all the time. They're things that we can allow to change and cause something else to change. And thinking about the domain of a variable is something that makes sense. So I can, if I'm talking about the domain in the box of candy situation, say, oh, well, the weight of the candy that I'm putting into the box can vary from 0 to, I don't know, maybe 10 pounds is the maximum that could fit in any of their boxes. Something reasonable. Just mathematically speaking, 0 to infinity makes sense as possible amounts of candy, but to fit in a box, maybe 0 to 10 would be a sensible domain. And all the real numbers of pounds of candy in between. On the other hand, thinking about things that are parameters. A parameter is a letter, it could be a notation also, that represents a value that stays constant within a given situation. What I mean by that is, well, we use the letter M to represent a constant rate of change. It stays constant within one problem while we're talking about it, like the 275 per pound for the box for the candy situation, or the 0.75 meters for the flag. But like at the candy store, you could go get a different sort of candy or snack mix, and maybe it has a different rate that they charge for it. But while you're filling up the box, the rate doesn't change on you. It stays that same one value throughout the situation. So you can use letters to represent that. The M that we've used is a parameter because of that, thinking about that. It takes on one value at a time and stays that way. In y equals mx plus b, x and y are the things that we think about varying. M and b can change from one line or one relationship to another, but for any one specific graph, those have one value. There's supposed to be a number in those spots if you're talking about one specific linear relationship. Now, a constant, on the other hand, is a third item. Constants are things that, rather than referring to the slope as a constant, we can say that the slope is constant, and we can use a letter M to represent it if we needed to, abbreviate. If we're talking about a constant, as in a mathematical constant, a known constant value, c, the speed of light in a vacuum, square root of 3, just the number 12.7, that isn't something that changes from situation to situation. 12.7 is 12.7. E, it could be a symbol that we use, like pi, e, two irrational numbers that we've designated symbols for so that we can refer to them exactly without having to write anything else out. Just a little bit more complex version than what we do with square root of 3. Writing this symbol over the 3 because in decimal form, something that some people call real number form, that's not better. This is exact, this is approximate. Here's how we can write it exactly. We use this to represent the number that when you multiply by itself makes exactly 3. So in any case, these are constants. We use symbols or letters to represent quantities that are fixed for a while, at least, as parameters. And symbols or letters that represent changing quantities, those we call variables. So think about this situation. A cylindrical enclosure, or a tank, is used for raising fish. One particular tank has a depth of 5.4 feet, a radius of r feet, and is being filled at a rate of 17.9 gallons per minute. So, thinking about this list of 9 items, each of these could be talking about a variable, a parameter, a constant, or something that isn't any of those. There are other sorts of things. But V, the capacity of the tank in cubic feet, well, this one particular tank has a depth of 5.4 feet, a radius of r feet. I don't know what its height is, but whatever this tank is, as I fill it, it's not the capacity of the tank that's changing. It maybe how much water is in it. V, the total capacity or total volume of stuff that could fit in the tank, that's one number when we're talking about one tank. So this V is being used as a parameter. Number 2, pi. Use that on the last page. Pi is a mathematical constant. Not everybody knows it, but pi is a constant that is, I should say, well known. 5.4, the depth of the tank in feet. It's not a parameter. So if I said something like d, the depth of the tank in feet, the use of that symbol d would make d a parameter because the depth of the tank isn't changing. But 5.4 isn't a mystery. It's one specific number. It's, in this case, it happens to be the depth of the tank, but 5.4 isn't a parameter because it is just one single number that has one particular value. I can't change the value of 5.4 to be something other than 5.4. So r, the radius of the tank in feet. that was given in the problem. You can see, well, thinking about a tank, this R isn't changing. If it's a cylindrical enclosure, the radius is one number all the time. Now we don't happen to have that number, it's just called R, but that means that this one valued symbol here is a parameter. So look at number 5. Do you notice that it's A, talking about number of fish in the tank, which wasn't mentioned above. Kind of weird, but also notice there's not a symbol. The number of fish in the tank. If you're just thinking about how many fish are there in the tank. Maybe there's a few one day, then they dump a bunch more in the next day, then they harvest some to take them to whatever they're using the fish for. So the number of fish in the tank could vary. But what I'm not going to do is say that the number of fish in the tank is a variable. It's a varying quantity, but a variable has to be a symbol or a notation. So this is like a concept or a definition. If I said n, the number of fish in the tank, then n would be a variable, but I need to have some sort of symbol or notation, a letter, to call it a variable, as opposed to just saying that this is a quantity that's likely varying. H, the height of the water in the tank, in feet. Oh, well, we're filling the tank at 17.9 gallons per minute, so unless there's a hole in the bottom of the tank, then this H, the height, is going to be changing. So the height of the water in the tank in feet is a changing quantity, and H is the symbol we use to represent it. So H is a variable. Similarly, lowercase v, number 7, the volume of the water in the tank in feet cubed, cubic feet, would also be a variable. V sub n, the volume of the water in the tank at noon today. That's talking about one specific value of the volume, and that's not changing. Whatever it was at noon, that was what it was at noon. And so this is a parameter, a symbol or notation used to represent this one specific numerical value of volume. That makes V sub n a parameter. And, well, number 9, same kind of problem as number 5. The tank's filling rate in gallons per minute, that is a constant quantity. It's 17.9, but I don't want to call this a constant because the tank's filling rate in gallons per minute isn't a symbol. It's not a number. It describes a constant quantity, but it doesn't say 17.9. It's also not a parameter because it doesn't have a symbol for that. So this is just none of the above. It's not quite a parameter, and it's not a constant. We're missing a notation or a number. If it said 17.9, the filling rate in gallons per minute, that would be a constant. If it said F, the tank's filling rate in gallons per minute, that would be a parameter. But as it is, it's just the definition part, so it's neither. All right, so things that are variables have domains. Things that are parameters and constant only have one value, so we're not, or one value at a time, so we're not necessarily concerned about those. The domain of each that's a variable. So variables, only these two, 6 and 7, right? So the height of the water in the tank in feet. Well, height of the water at a minimum would be 0. At a maximum, let's see, the tank has a depth of 5.4 feet. So H then, the height of the water in the tank, would have a domain that includes all real numbers from 0 through 5.4. And V, the volume of the water in the tank, also minimum value of 0, and goes through, well, an expression for it. We don't know what the radius is, but the volume of the water in the tank would have a maximum of pi r squared times the depth, 5.4, that maximum. So 0 through pi r squared times 5.4. But r is only a parameter. Whatever it is, however, for any one given tank, that same expression would give us the domain for the volume. All right, So moving on, functions and function notation. Quick review from algebra. If I have the distance that a motorcycle travels from an intersection, and we're measuring that distance in miles and the time in minutes, let's talk about the relationship between minutes since it left the intersection and miles since it left the intersection. Let's call that relationship G. Maybe it is or maybe it isn't a constant rate of change. So this is not a continuation of just constant rate. Motorcycles can speed up and slow down, and they do that a lot, especially when they just left an intersection. So not talking about dy equals mdx, just relationship in general. If I say g of 8.3, thinking about what this means, g is the relationship between the distance and time, distance that the motorcycles traveled from the intersection, time elapsed since it left the intersection. When you see this notation, make sure you think about what the meaning of it is. The 8.3 here represents the independent variable, a specific value. G of 8.3 represents the dependent variable, one specific value. It's a representation of it, not a value for it, but this G of 8.3 represents then, in this case, a distance traveled after 8.3 minutes. The distance would be given in miles. So the number of miles is G of 8.3. Don't know what that is. How many miles is that? 3 miles? Half a mile? Was it lots of traffic? Were they speeding? Did they go lots and lots of miles? But regardless of what it is, G of 8.3 represents a number of miles. G is just the name of the function, or this is what cues us in that we're talking about this relationship between, as it's defined up here, distance and time. And then the number inside the parentheses, 8.3, is the value of the independent variable. So this is 8.3 minutes. So even if you have a formula, a function rule written out, something that defines the computations that relate the independent and the dependent variable, because again, f of x is how I find a value of a dependent variable when x is the value of the independent variable. And then here's a formula for that, for what I do with x in order to get this dependent variable. Now, keep in mind though, if I say f of 2, I don't have to substitute in, compute something. F of 2 on its own just means the value of the dependent variable, maybe a y value, when x is 2. If there's not a story to go along with it, we can't translate it as much as we did the last time. But you don't have to think about, oh, let's substitute in and get an answer, per se. We're just talking about this is the dependent variable, f of 2, that corresponds to the independent variable, value of 2, when we use the relationship f. So f of 2, or using function f with independent variable value 2, gives us dependent variable value f of 2. So looking at this notation, let me just throw in some stray letters. Suppose that two quantities are represented by y and p. P is a function of y according to this function definition. Z of y equals 3y squared plus 8y minus 17. So this is our dependent variable. Can be computed using this formula with an independent variable called y. Up here it says two quantities are represented by y and p. So thinking about words related to functions, just to make sure we're on the same page here. The function definition, looking up above, a function definition is something that shows someone what is the relationship. So it's the whole thing up here, this whole expression, z of y equals 3y squared plus 8y minus 17. This tells us that our function is called z. I get a dependent variable using this relationship z by doing this computation. What about the dependent variable? We could call it z of y. Z of y is a value of the dependent variable, but there's another option for us given by the sentence or phrase up above. We could also call it P. So z of y or P. Either of those represent the dependent variable. The name of the dependent variable, however, according to this, is apparently P. The independent variable is y. That's the one that's in the parentheses. You can think of it as input independent in the parentheses. But keep in mind, when you see this phrase, P is a function of y, that means P is the result from having used independent variable y, or independent variable, dependent variable. P depends on y. The function name is z. Z isn't a variable, z is the name of this relationship. Now, function rule, this one can be a little bit confusing. Function definition and function rule sound a little bit the same, but function definition is a complete defining of what's the name of the function, what's my independent variable, how do I do the computation. The function rule is usually just said to be the right half of that. So just the computing part without defining and what do I call my result. Now the value of P, we said, well, oh, value of P is z of y. So z of y here is another way to talk about a value of P, or just to talk about P in general. So if someone were to write z equals 3, that's, I'll just answer this question since you're not here. Is z equals 3 a valid statement? Well, no, because z is a relationship between two variables, so this doesn't describe a relationship between two variables. But if you can imagine somebody that's speaking too quickly, being imprecise, maybe what they meant was that z of y equals 3, or z of some number equals 3. Z of y equals 3 for some particular value of y. Or p equals 3. P is another way to write z of y. But z can't equal 3. Z is a relationship. It's not a variable that can take on different values. All right, so quickly then, once talking about this, I said, in the last statement, I said something, a P depends on y. In order for us to have independent and dependent variables in a function, the dependent variable actually has to depend on the independent. Specifically, thinking about something that functions. I hope your phone functions. If you're trying to make a phone call, you get to choose what number you dial, and as a result, somebody's phone rings. We hope they pick it up. Person, company, whatever it might be. And if everything's working as planned, when you dial a specific number, you get the person you expect. So if you dial this 784 number, you get Visa. If you dial this 699 number, you get your friend, etc. So if you get the number or the person you expect, and not because you're just mixed up people's numbers, then you'd say your phone is functioning. Each of these numbers determines exactly one person. Now, it doesn't have to be exactly this way for a function to exist, or for your phone to be functioning, because if you dialed, one number, like for instance, if Visa customer service, they probably have, in reality, thousands of phone numbers that get to them from different area codes that are listed as local or whatever else. And so Visa customer service could have all of these numbers go to them. Now, that doesn't mean your mom doesn't have a number, it's just maybe it's something else. But for each value of the independent variable, the dependent variable must be uniquely determined, meaning if I have one particular phone number, that has to pick one particular recipient of my phone call, or at least one particular business. It could be a different person answering the same phone. But if sometimes you got pizza and sometimes you got mom using the same phone number and you just had to hope for the best, or like see if it's Tuesday, then something happens, that's not what you're hoping for. One choice, one independent variable value, should only have one result. Or in other words, kind of asking questions that have only one answer to them. So you don't want this sort of relationship between input or independent variables and output or dependent variables to happen. If you choose an independent variable value, there should be uniquely determined one, at most, dependent variable. What I say at most is you could dial a number that says this has been disconnected and there's nobody there, or other sorts of this number doesn't work in this function. But in any case, let me move this thing out of the way, possibly. There we go. You get a new phone if this sort of thing happened. However, what I said earlier, like your friend could have two phone numbers, maybe a cell phone and a landline. You can get a hold of them either way. Visa customer service probably does have thousands of numbers. That's okay. As long as the same one phone number would get you Visa customer service every time, that's okay. But if sometimes you tried to call them and you got your ex instead, that's not a function. So this relationship between independent and dependent variables is specifically called a function. Other things are relationships that are perfectly valid. We can write things about them. They just aren't called functions. And we don't want to use function notation with them otherwise, because that can be then vague. If I say f of 3, and f of 3 is sometimes 5 and sometimes 9, that's not a useful notation to be describing that dependent variable if it maybe it's one thing and maybe it's not. So this arrangement with multiple phone numbers for the same person is a valid function. One phone number leading to optionally a few different people is not a valid function. So on the sheets of paper that I handed out in class, which are also posted in Canvas, you'll see questions about cars, and this is a race car leaving a pit stop, and a function called D, or we've got D is a function of T, a dependent variable D, independent variable T. And there's some questions about this, and the bottom is writing out what's the meaning of all these expressions. We'll have a little bit of time to compare notes and look at these together in class on Thursday, but this is something for you to think about now. It is posted in Canvas, like I said, in the handouts and class information for Module 1. And we're also going to look at height of the water in a sink, and there's a bunch of questions related to this, which we'll go through all of this in class on Thursday. But this is using function notation. The other thing that we're going to do in class Thursday is look at the other document that I posted that's about sunflowers and heights, and what that is, that's practice at using some certain commands related to graphs and functions and function notation in GC. And by the time I see you Thursday, you will all have had recitation. So in your recitation, you talked a little bit about GC. We're going to talk some more about it so that you understand how to use it. And so throughout the course, you can use it as a tool to assist with visualizing, to do some computations, to analyze graphs, and to be able to see the relationships that we're talking about dynamically. All right, that's it for today. So I'm going to post this. It'll take a little while, but I hope you get it before dark tonight.